So in the third presentation here, what I want to do is to make a link between these two portions of the previous, well, the two previous lectures. This is lecture 1, and this is lecture 2. And so what we can do here is we actually link these two concepts and the conclusions and the ideas that we had from these first two lectures into this what's called an integrated rate law. And essentially what the integrated rate law is doing, it's going to generate a set of equations, and they're going to make a connection between the concentration of the reactants versus the time for the reaction. You know, if you remember, the graphs that we saw from the previous lectures, we had this kind of relationship occurring. You know, we start out with the initial high concentration. As time proceeds to the right, as the reaction goes forward, and the decrease in the reactant concentration. And what we do here is we're going to set up a couple of different equations, one for the first order and one for the second order reactions, so that we can really calculate the concentration of the reactants at any given time in the future. On the previous slides, we had, you know, data corresponding to the change in concentration with time as empirical data. And so here we're going to actually be able to predict the concentrations at any time after the reaction starts. And also this method allows us to predict whether the reaction that we're looking at, just based on the raw data, we're going to manipulate this data based on these equations, and we'll be able to predict whether it's a first or second order reaction. So keep that in mind as well, and we'll see both variations of that as we go through the talk here. Now this is an equation or a reaction that we saw from the second presentation. This is a classic first order reaction. This is referred to as a isomerism of a methyl isonitrile to acetonitrile. And there's a single what's referred to as a transition state that it has to go through to get to the product side, and it's governed by first order kinetics. And so what does that mean? Well, you know, we have the reagent. There's only one reactant here, and so what we can do is we can draw this conclusion. And this is the first one that I want to look at. This would be from the second lecture. And then this part up here is from the first lecture. Like I said, we're going to combine these two together and make the connection here. This would be the empirical data for the reaction as it proceeds through time. And you can see the different data points being plotted against time there. And one thing I want to point out is that it doesn't matter whether we use partial pressure or the concentration of the initial reactant. Either one of these are going to work. And I'll show you a variation of both. The 10th edition Brown-LeMay, if I'm remembering correctly, only deals with the concentration here, but at any point of those equations that we're going to develop here, we can interchange the partial pressure of the reagent to the concentration of the reagent, depending on what data is given to us initially. For example, for this particular example, we start with the partial pressure of the reagent, and we watch as that partial pressure decreases over time. Okay, so you know, this was the rate law that we generated from the second equation. We have our rate constant and the concentration or the partial pressure. Again, I'm going to be using this one for this particular talk. You know, in the first lecture, there was a connection being made between the first and second one, where this idea of the rate is actually described by two different equations depending on the type of data that's given to you. You know, this one was what allowed you to calculate the average rate and the instantaneous rate, and then this one was acquired by really a different set of data than what you see here. It was a series of different reactions where you're varying the concentration, you're following how the rate changes for each of those different examples. So that's just a reminder of what we've already done in the past two lectures. That builds up, if I'm saying that these two expressions are, we'll say, quantitatively equivalent, then what it allows us to do is to take, this portion and that portion and say, well, if the two rates here from the first and second lectures, if they're quantitatively equivalent, then we can make this relationship. We can say, well, these two are going to be equal to one another. And what the book goes through, and what I'm going to go through a little bit here, is just showing you a little bit of the mathematics that's involved here. Now, you need calculus to actually give a full treatment of this, and I'll give you little pieces of the calculus, but we're not going to be doing integration here. I'm just going to show you the conclusion that we get from the mathematical treatment. There's a couple terms here that I want to go ahead and throw out because these are commonly used in this type of kinetic study. This is referred to as a differential rate law. And what it's doing, it's relating, well, the change in pressure to the change in temperature. And by using this equation and applying some, again, mathematics is really beyond the scope of the course. I'm just going to sort of put some pieces together here. I'm going to rearrange this expression. I'm going to collect the partial pressures on one side and then bring K and delta T together on the opposite side. And what we see here is the partial pressure for the reactant divided by the partial pressure of the reactant is going to be equal to the negative of K as the temperature change. And again, it's just some algebraic manipulation that I'm doing here with this this relationship that we established from really the first two lectures. Now, this differential rate law, we can actually convert it to a form that allows us to do the calculus here. And notice, let's see, I am changing the notation just a little bit to clean it up a bit. I'm substituting, instead of rewriting that every time, I'm just saying R, the reactant. In some ways, I'm trying to set it up as almost a generic first-order equation. Any first-order reaction is going to be related. The rate law is going to look like that, where it's just a concentration of one reactant affecting the rate of the reaction. And so by using the little r, again, I'm trying to, oops, that should be a p. I'm trying to make this more of a general case for us. Now notice I've changed the delta here to a d, and again, this is a mathematical operation. It's an integration that we're getting ready to do. And if you don't understand the full mathematics here, it's okay. If you've had some calculus and you if you sort of recognize some of this, it'll be maybe useful to you just following through the manipulation that I'm doing here. But again, it's not essential that you understand the calculus that's going on here. What I'm doing is I'm integrating this expression over, well, this is the initial partial pressure, or the initial concentration. Again, the book uses a concentration, but they can be interchangeable. And the initial, the way we know that it's initial is that we're using a sub naught there, a 0 at the bottom. And then this means we're integrating this expression from the initial concentration to a partial pressure at time t. So t is equal to some time during the reaction. And then the 0 time is here to, again, time t is the same value here, the dt. And we don't get a quantitative value here, we get a new expression is what we do. And again, this is where our calculus comes in, and the mathematics that really is beyond the scope of the course. If you want to know more about it, we can talk about it outside of class. Or I guess I should say in class if you want to. And that is a mathematical formula that is obtained through the calculus here. And this is really what this form is, what we're going to be using. I mean, we're going to be manipulating it quite a bit, but this is the form that we're going to be using. And this is referred to as the integrated rate law. This is the expression that, again, notice what it's doing. It's relating the partial pressure of the reactant at any time t with the initial partial pressure, and then there's that time t showing up in this other side, on the other side of the equal sign, and then the rate constant is also showing up there, which we've already dealt with. And this is the integrated rate law for a first order reaction. You know, there's only two types of kinetic reactions we're looking at: first order and second order, and we're going to generate an equation for each one. And so this is the one for our first order reaction. And I want to manipulate this a little bit further. I want to put it into the form of a line. So let me redraw this. Again, there's some algebra going on here, and once I rearrange this expression, I get this new form. And this is typically the form that you see in a lot of the textbooks. And just a note, the way I'm breaking apart this natural log function, if you have, and there's a review of this in the appendix for Brown and LeMay. I guess a mathematician would call this a natural log identity, I believe. I'm not sure, but it's a mathematical method to break apart natural logs. We saw and whether it's natural log or log base 10, which has that notation, it's the same kind of procedure. So we have dealt with this a little bit before. And it allows me to break apart this expression and then rearrange it in this particular form. What is the advantage of this particular form? Well, again, there's our initial conditions. There's time, which we're always interested in a kinetic reaction. Again, we're trying to relate, you know, what happens is reaction over time. And then, you know, that what is happening is actually given by the partial pressure. So this would be the partial pressure or concentration. Again, they're interchangeable pretty much. The partial pressure of the reactant at any time equals t. And so we're not, you know, if we look back here, the times are just very specific data points. Well, now that I'm saying, you know, like I said, any time t in the future, then what it allows me to do is to predict, you know, not just the time in between the data points, but also any time in the future. And so I know exactly what's going to happen to the reaction in the future. It's almost like applying Newtonian mechanics to a chemical reaction. You know, the notion of Newtonian mechanics for a macroscopic world is that, you know, if you know the initial state of a system, then using a certain equation, you can predict everything about that system at any point in time. And that's essentially what this expression is going to allow us to do. And on top of that, it has a predictive property as well. Using this expression, we're going to even be able to predict whether a set of data corresponds to a first order or a second order type reaction. And that's actually shown, that's why I converted it into this particular form. If you look at the next slide, what I've done here is to remind you some information. It may have been a while since you've seen this, but this down here, this is the equation for a line. On a graph where x and y, well, simply x and y, the data points for the graph, and then m equals the slope, and then b is the y-intercept. And just a heads up, if you don't know how to do this, if you don't know how to plot data on Excel, there is a tutorial. There is a procedure that's listed in our lab books on page 412. And you'll use this for this section. You'll use it for one or two of the labs. So it is something that you need to get accustomed to. Okay, so let's take a look at this expression and how is it used. Well, again, this is just the raw data that we've seen before. You know, if we were given this data back in the first lecture, then we could, you know, determine the average or the instantaneous rate from this particular graph, and that's fine. We can do that. But in the context here, what we're doing is we're recognizing, well, here's our partial pressure data corresponding to different points in time. Again, it would be given in a data table. There's an example coming up here in a minute of that. And if we take the natural log of these different partial pressures and plot them now with respect to time, notice that we have a straight line at this point. And again, once we have a straight line, really the important point here is that we are going to be able to calculate the rate constant for this particular expression just by looking at the raw data here and how it plots out for this particular equation. And once I plot this out and I set the trend line in Excel, what it does is it's going to give me an M value. A slope is equal to negative 5.1 times 10 to the negative 5. And the units here for first order reaction is inverse seconds. And then notice, like I said, the relationship M equals negative K. Well, if M equals negative K, then I only have to change the sign here to then establish what my rate constant is. So it's another way that allows us to calculate the rate constant. We saw a method to calculate the rate constant from the data in the second presentation as well. Now just keep in mind that the difference here, it's the same rate constant, mind you. You'll get the same numerical value for the rate constant, but here all we're doing is we're taking one set of raw data and then we're converting it into this particular form. Again, if it fits to a straight line, then we know it's a first order reaction. That's important to note. Back in chapter 2, what we had to do is, or I'm sorry, lecture 2 for this chapter, we had to have, you know, at least 3 or more different sets of reactions and go in there and start interpreting how the rate changed with the concentration change of the reactant to be able to determine what the order of the reaction was as well as the rate constant. And so this, again, you're just taking one set of raw data and converting it into the straight line to calculate the K. And so it requires a little bit more computer work in the sense of working with Excel or whatever linear regression program you prefer. Scientific calculators these days, graphing calculators, have the ability to do this. So you can determine it that way as well. So this is just another tool to determine, again, the order of the reaction as well as the rate constant. Now something else about this reaction or this method that allows us to gain some information about the particular reaction is something called the half-life. And you can see here's a definition of half-life, here's a comment about the half-life. All this is talking about is, you know, what is the time t that it takes for the concentration to be cut in half, essentially. And what it is it's a convenient way to describe the speed of the reaction, if you will. And if at each half-life, you can, we'll quantitate this here in a second, but you know, this is one half-life, this is two half-lives, and you can see that at each corresponding step, you reduce that concentration by half from the y-axis. So I will say that this is the same data as the previous graph, same data as this particular graph. The scale is just a little bit different, so it highlights the half-life of the expression. Now and we don't do this graphically. I mean, I guess you can plot it out and go to half the concentration and then look down on the x-axis to figure out what the t1/2 is going to be. So the half-life is given that particular notation, and we'll see it as I go through this little derivation that I want to show you. But there's also a mathematical expression for it, which honestly is more convenient and probably more accurate. Whenever you take a graph and you sort of approximate the positions here on x and y, there's always some experimental error, if you will, that gets introduced into that process. Okay, all I'm doing is I'm algebraically manipulating the expression. Now, just mind you, I'm not going to ask you to do these algebraic manipulations. I just want to sort of show you little pieces of the puzzle, little stepping stones along the way, if you will, and so you can appreciate a little bit of the method here, a little bit of the manipulation. Actually, what I'm doing here is I'm using, remember this identity, this relationship that I talked about here? Well, I'm just going backward and I'm resetting the expression, and you can see it here with the PT over P naught. Now what does that half-life represent? Well, mathematically, one would say if you're talking about T1/2, the half-life, that particular time that we'll calculate here in a second, this would be T1/2 here. Well, at that particular point, what's happened to the concentration of the initial value? The initial value is cut in half. And so the expression that gets inserted into this formula is this guy here. So again, what I said is that the partial pressure at T1/2 is equal to 1/2 the initial concentration. Well, what it allows me to do is to change my notation for PT up here. And so what it will look like, if I just plug that expression in here, it's the only thing that changes. I guess along with the, notice I am introducing the T1/2 here just to remind us that now we've transitioned into a half-life formula. P naught over P naught, that's going to cancel out actually, and you're going to be left natural log of 1/2 equals negative K T1/2. The typical rearrangement of this, if you take the natural log, that's actually equal to 693 over K is equal to T1/2. And I'm keeping the negative sign because that doesn't get dropped during the calculation. I'm sorry, I misspoke here. Actually, yeah, the negative sign is followed through. The natural log of 1/2 is actually negative 0.693. So these two negatives are going to cancel out, and you're going to be given a positive value here. And this is the expression that we use to calculate these values, these T1/2 values. And so if I just plug in the values from the results earlier, remember that rate constant, it was the slope that we determined, 10 to the net minus 5 inverse seconds. What I get here is 1.4 times 10 to the plus 4 seconds. And that does correspond to the value that you see here. And then if you double that, then you get the second half-life, which is, this would be, down here would be 2.8 times 10 to the 4 seconds, and so on and so on. And so again, it allows us to predict sort of the speed of the reaction. How fast is that reagent actually going to disappear in this expression? Now just I want to do one more here, that hydrolysis reaction from before. It was given, this is from the second presentation. I'm not going to go through the full treatment here. You do see that exponential decay for the reagent. This is the raw data. The rate expression that we figured out before, it was dealing with that organic reaction that I talked about. First order reaction just with respect to the organic reagent. I'm going to rearrange this just and put RCl just to make it a little easier for the formulas here. And like I said, whether it's concentration or partial pressure, if we know that it's a first order reaction, then we can convert this kind of expression, and it's describing, again, it has a predictive quality of knowing what the concentration is at any point in time, even days later, if you will. If I take the raw data, and again, remember, we can always, if we plot this on the y-axis and then time on the x-axis, what we see in this next graph, and all I'm doing is I'm taking the raw data here, taking the natural log of it, and now you can see the new values at this point. I do get a straight line, which does correspond to a first order reaction. Here is this is coming straight from Excel, this graph here, and then this is the equation that it's going to give you. And there's the slope, the m, right there. Y-intercept we typically don't use. One comment about r square. If r square is 1, that means it's a perfect line. I'll just comment here. It's very rare that empirical data gives you a perfect line. I'll just say that right now. So this data is either really, really good, or it could have been possibly made up just as a example for us here. Honestly, I can't remember where I'll pull that data from at this point. But all I'm doing again is plotting what you see here. Natural log of the concentration versus time. Straight line tells us it's a first order reaction, which we already knew. And then the slope here tells us K. So the K here is going to be, and I'm going to bring out one more significant figure here just for convenience. Gives us the rate constant, and just like before, we can then talk about the half-life. Remember the equation for the half-life of a first order reaction. Notice it's independent of concentration. It actually doesn't matter, how high on the y-axis you actually start. It doesn't matter how much of the reaction actually is in there. The rate of the reaction is independent of the concentration. It's going to be the same rate at each time. Or I should say the half-life is independent of the concentration. And so it allows you to just simply plug the rate constant from the graph into the formula here. And let's see, this is 0.0020. And we get a half-life of 350 seconds, and that does correspond roughly to where I've drawn the lines here using the raw data. So notice this is the raw data. It's not the manipulated data that we saw from the last slide here. It's not that guy. And so again, it's just a sort of a quick and dirty way to sort of gauge how fast this reaction is actually proceeding. Now, one more example for the first order reactions. It's one that we saw at the very end of the second presentation. Now I'm going to abbreviate this DME. I don't know if it's a common abbreviation that chemists use, but I'm going to use it here just to clean up the expression a bit. We're given that it's a first order reaction, and so the conclusion that we can make is that, well, if we know it's a first order reaction and there's only one reagent here, and so the progress of this reaction is only dependent upon this one compound, DME. If I take that integrated rate law that I developed a few slides ago, again, it allows me to predict what is the concentration of this particular ether at any time in the future, given the rate constant of the particular first order reaction. And again, appreciate the fact I did partial pressure initially, I did concentration for that last example, and I'm doing concentration here as well. Partial pressures and concentrations are interchangeable here. The only difference is the units are going to be different. Oh, actually, we're in torr, so it's not going to hurt me. I am going to, let me introduce some notation that I use a lot. So DME, our ether that we're talking about, at the initial time, the naught here, and then the time t here. So again, we can predict what is a partial pressure at any time in the future as long as we have, these three values given. And we do have that. We have the K at this point. We have the initial pressure here, 135 torr. Excuse me, and we want to know the partial pressure after, 1,420 seconds. And so, really, all we have to do once we have this expression is to plug and chug and see what our value is going to come out as. Second inverse. The time is, and natural log of 135. I'm going to drop the unit here just for convenience. This is still the natural log of the partial pressure, DMF. And actually, I could change this, but time here, the T now, we know what time we want to know about. This is 1,420 seconds into the future. And so this is just, it's just a standard kind of calculation. You get 3.9 at this point. This is still natural log. On your calculator, the natural log, you would take the exponential of both sides here, and I'm going to have to, let me erase that and make it a little bit neater. Exponential of 3.9. So the exponential, if you take the exponential and natural log, you're just canceling that out essentially, and you get DMF at time t, and then that value is 51 torr. And so again, if we were looking at raw data and we started at 135 torr here on the y-axis and time here proceeding into the future, we would see that kind of exponential decay. And then again, this equation allows us to calculate the value at any point in time. And so this one just happened to be, somewhere about 1420 seconds or so. But that value could have been anything, to tell you the truth. So it's just another example of how you can use this particular expression to predict values for kinetic reactions. Now, that's the run through for first order reactions, and second order reactions are very similar to first order reactions in terms of the treatment of the data. Okay, so I've pulled a sample exercise 14.8 from the 10th edition of Brown and LeMay. Here's the equation, here's the raw data, okay? And again, this is the first lecture, this is the second lecture, established the relationships here. Now again, I'm working from the perspective that I know this is a second order reaction. If there's only one reactant originally, to make it second order, it means it's brought to the square here. Now, actually, I think the way this sample exercise is actually set up is to use the two integrated rate equations to prove that it's a second order, predict that it's a second order reaction. Okay, so I'm telling you the punchline, if you will. I'm telling you the answer from the beginning, because what I want to do is I want to take this expression now and note I'm doing the same thing as before. Whether I'm in lecture 1 or 2, the rates here, the description of how this reaction is going to proceed in the future, these rate values are going to be quantitatively equal. So it allows me to set this value, this expression equal to that expression. If I go through the same kind of here it is now. If I go through the same kind of calculus and the same kind of rearrangement reactions, the expression that I get at the end is going to look different than the first order, which is, it's a different type of kinetic, so you should expect it should look different than the first order. And again, my goal here is not to teach you calculus. My goal here is to show you how to use these particular expressions. So again, there's a bit of algebra, a bit of calculus, and some more algebra that gets me to this particular expression, and this would be the integrated rate law for a second order reaction. similar form takes on here. We're dealing with just the particular reactant at some time t. The naught still means initial concentration. And then there's our t, and there's our rate expression. Now, note this little point, and it's shown on the next graph here. This is in the formula for a straight line. And again, that should be a plus there. So what am I doing? Well, that means that if this indeed is a second order reaction, if I plot the inverse of this is the raw data, if I take the inverse of that, which is shown in that last column of the graph here, or the table, and this is pulled from that sample exercise in the book, and if I plot that data with respect to time on the x-axis, and it's this plot here, then notice what I have. I have a straight line. That kind of graphical approach, if you will, that kind of data manipulation that you see here is telling you that it's a second order reaction. You can, again, just like I said for the first order integrated rate law, you can take the raw data, manipulate it just slightly, do the plot, and then do the trend line here, and if it's a straight line, then it's telling you it's a second order reaction. Now, the reason why they have this third column of data here is that this is testing. This is testing for a first order reaction, and it fails. Notice that if you plot the natural log of the raw data versus time, this is not a straight line. You can see there's a slight bend in the data for one thing, and then if you try to fit a straight line to this particular expression, your R square value is going to be less than 1, let's say. It'll probably run somewhere between like 9.8 or lower, something like that. Really, for an R square value to be valid, I would say at least 2 nines, 3 nines would be better. That's the typical kind of data that you see. And so once you start getting below 0.98, especially if it's 9.6 or 9.5, it's telling us not a straight line. You have to be pretty close to 1 to have this data be reliable. And that's the kind of pattern that you're going to see for most of the problems that you're going to get a hold of. And just like the first order reactions, this straight line, by plotting of this data, confirms that it's a second order reaction, okay, which again for us was already given, and then also, allows us to calculate the rate constant here. The rate constant for this particular reaction would be 0.543. Let's see, units for second order is inverse molarity inverse seconds. So just like in the first order reaction, the first order integrated rate law, we can determine the rate constant just from the raw data. And we don't have to have those multiple sets of reactions to be able to figure out that particular value. And, as you might expect, well, what do you know? Half-life is popping up here. And again, half-life can be used as a measure for, about how fast is this reaction going. The raw data is plotted, and this isn't, I will say, this isn't quite an exponential decay for this one here. It looks like one, but it's not quite, without getting into the details of the mathematics, which I'm honestly still a little fuzzy on. But anyway, I plotted in red. We'll go back to it here in a second. Again, what are we doing for these half-lives? We are, changing t to t1/2, so the notation here is going to be altered a bit. And then again, what does that mean? That means that, we're starting out, the initial pressure gets transitioned to half of the, at t1/2, then the initial pressure has been cut in half. And so, just like I did before, there's a little bit of a change here. We say that the concentration of the reactant at time t, and this time 1/2 is 1/2 the initial concentration. Halfway down on the graph on the y-axis. And again, you could do it a graphical way by drawing lines and seeing where it shows up on the x-axis, but there's always a little bit of error if you're using just the graph that's in front of you. Instead, if you plug this expression, plug this into that portion of the expression, and then solve for t1/2, what you get now is this expression. And honestly, I'm leaving out a lot of the algebra because it's not something I'm going to ask you to do. This is what I'm going to ask you to do. I'm going to ask you to calculate the half reaction for a second order reaction, or the half-life, I should say, for a second order reaction. You can just simply use this particular formula. We know the value for the rate constant, 543 inverse molar, inverse second, and then the initial concentration. Well, it's just given from the raw data. You can see it here, 0.01. And I'm going to, the initial data is actually taken into, well, there's 4 significant figures here. So let me just include that in the expression here. When Excel plotted this, it didn't factor in the sig figs there. That's in molar. If I plug in chug, then it tells me that it's 184 seconds, which, notice that the line here is coming in just below 200. So it is consistent with the graphical method that we see up here. And this is, of the 4 reactions that we've seen in this particular presentation, this one is the slowest under the conditions given. I'll put it that way. So again, these integrated rate law allows us to predict what the order is, and then also allows us to calculate the half-life, and then something about the reaction mixture at any point in the future. Same kind of example here as we saw in the previous example, if I can find it. Yeah, this first order reaction. We compare what I did here with what I'm about to do. I have the K value here, the rate constant. I have the initial concentration, which note is different than the last example, so that value is changing. And then I have the time at 30 minutes, a half an hour. Now, one thing to note is that the unit on our rate constant is in inverse seconds. This is in hours. And so the first thing we want to do is to convert that to seconds. And that is equal to 1800 seconds. And now we're ready to just plug it into this expression. Again, my goal is to, what is the concentration of the NO2 at some given time in the future? And again, this given time is 1800 seconds into the future. And now I have values for these 3 quantities, and I simply just plug them into the expression. And I'm going to run out of room, plus the inverse of the initial concentration. Once I calculate all this, I get 997.4. That is going to be inverse molar if I factor in all of my units there. And then now what I have to do is, well, to get the denominator on top, I take the inverse of both sides. 1 divided by this number is the mathematical operation. And we get 10 to the minus 3 molar. And so again, it's very Newtonian in the way it can predict the outcome of these reactions. We have a given reaction. We know it's second order. We have an expression that describes, that relates the time to the concentrations of the reactant that matters, if you will. And then by just simply plugging and chugging the different values, it allows us to predict, what is the concentration of this reactant at 1800 seconds into the future. Okay. And those are the basic operations that you need to be able to do for this section of chapter 14. Okay? Thanks.